Hi, I'm Professor Goins. In this video, I'm going to look at some basic properties of the cosecant function. In particular, we're going to look at the definition, some function values. We're going to look at how to build its graph. We're going to look at some properties of the function based on the graph, and then we'll look at some other examples where we do some transformations of it. First and foremost, the cosecant function is the reciprocal of the sine function. In other words, CSC is the abbreviation for the cosecant function. That's the notation we use. So the cosecant evaluated at x is the reciprocal of the sine function evaluated at x. All right, in particular, the cosecant of pi over 2. This is 1 over sine of pi over 2. And what's the sine of pi over 2? Well, remember that the sine is the y-coordinate on the unit circle corresponding to that angle. And pi over 2 being a quadrantal angle, meaning its terminal side lands on one of the axes. Pi over 2, more commonly thought of as 90 degrees, has the terminal side lying on the positive y-axis, which means the point on the circle is the top of the circle. That is a y-coordinate of 1. So sine pi over 2 is 1. And this is equal to 1. Okay. On the other hand, the cosecant of pi over 3, so this would be the reciprocal of the sine evaluated at pi over 3. Okay. This is not a quadrantal angle, so it might not be as easy to memorize, but it is one of the common angles that you will encounter, and it is 1 over, or the cosecant's the reciprocal of, so sine pi over 3 is root 3 over 2, which simplifies to 2 over root 3. And that's traditionally written where we rationalize the denominator, giving 2 root 3 over 3. Okay. Cosecant of pi, same idea, the reciprocal of the sine of pi. All right, that's another quadrantal angle, so that's one that we can reason through fairly quickly. Pi is half of a clockwise rotation, or half of a counterclockwise rotation, which means the terminal side lies on the negative x-axis, which means that the point on the circle is on the far left, and the far left of the unit circle has a y-coordinate of 0 because it's on the x-axis. That means that this would be 1 over 0, and of course dividing by 0 is undefined, so this is undefined. Okay. Now this is one thing that distinguishes these other trig functions from sines and cosines, is that they will have values for which they're undefined. They do have domain restrictions, whereas sine and cosine do not. All right, let's use some of this discussion right here, some of those function values, to build the function or the graph of the cosecant function. Since the cosecant function is related to the sine function, right, they're reciprocals, what I'm going to do is I'm going to start by looking at the graph of the sine function. All right, let's highlight the first and the third function value that we just came up with. The cosecant of pi over 2, that function value is 1, so that means the point on the graph is going to be pi over 2 comma 1. That means that I'm going to have a point on the graph. Let's use blue. The point on the graph would be right here. All right, let's highlight the function value, the cosecant of pi. It's undefined. So at the function value for pi, it's undefined, which means that there would be no point on the graph. And I'm going to, instead of putting like an open circle or something like that, what I'm going to do is I'm going to put a vertical dashed line to indicate that I cannot use that x value. All right, so along that same line of thinking, let's find some other x values that I cannot use. Well, if the sine function is 0, then I can't use that x value in the cosecant function because, once again, I have the same issue where I'd be dividing by 0. So everywhere where I have an x-intercept of the sine function, I have to eliminate that x value from the graph of the cosecant. Okay, so I have to eliminate negative pi, I have to eliminate 0, I have to eliminate pi, I have to eliminate 2 pi, so on and so forth. All right, let's pick another couple of values. At 3 pi over 2, the function value of sine is negative 1. Well, remember, to get the cosecant, I simply take the reciprocal of that. The reciprocal of negative 1 is negative 1. So that means that the maximum of the sine, that's going to be a point on the graph of the cosecant. The minimum of sine is going to be a point on the cosecant. Same story right here. Okay. Now let's highlight in between this maximum value and this intercept of the sine function. I know that this has a y value of 1. I know that this has a y value of 0. That means that somewhere in between here, approximately, let's say here, the y value is going to be 1/2, right? So if I take the reciprocal of 1/2, of course, that gives me a 2. And that would give me a point on the cosecant. If I were to go down here even farther, let's say approximately here, this has a y value, so at the tip of my marker on the sine graph, this has a y value of, let's say, 1/3. Take the reciprocal, and I'm going to get 3. So what's going to happen is if I take the reciprocal of all of these y values in between this dot here and this intercept, and I take the reciprocal of those, it's going to follow this shape right here. And it's going to keep getting closer and closer to this vertical dashed line, which is called a vertical asymptote, because I'm going to be taking the reciprocal of 1/8, 1/9, 1/10, 1/11, all the way down to, well, really, really close to 0. It's a calculus concept related to the idea of a limit, but we'll talk about that in the calculus course. But the idea is I keep taking the reciprocal of a small number is a big number. Okay, so just the reciprocal of a small number is a big number. Reciprocal of 1/2 is 2, 1/3 is 3, 1/4 is 4. So that means this graph is going to keep growing. And that same story is going to play out on all the rest of this graph. I'm going to do the same thing over here. Reciprocal of these smaller numbers are going to get bigger and bigger. Same thing over here. The reciprocal of these are going to get bigger, but they're negative. So that means that they're going to go in this direction. Same thing over here. Same thing here. Here, here, so on and so forth. So what we see is that we're going to get this pattern that keeps repeating out to the left and out to the right. Okay, just like the sine function repeats, the cosecant function repeats. Okay, so now let's use that graph and list a variety of really important properties of the cosecant function. So again, properties of f of x equals cosecant of x. First property, let's look at the domain. So the domain of the function. Domain is all the possible inputs. Well, we can see that the domain is fairly complicated to write because I have the interval between negative pi and 0, the open interval. Then I've got the open interval from 0 to pi, and then pi to 2 pi, pi to 3 pi, so on and so forth. So I'm going to write this a variety of ways. One way I can write this is it's going to be, well, I know that I've got, like I mentioned, I've got the open interval from negative pi to 0, union 0 to pi, union pi to 2 pi, union dot, 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 and that also goes in the other direction as well. So I've got this complicated union. There is a way that I can write this in a much more compact way using a slightly more sophisticated union notation, but I'm going to leave that off. If you want to see it, let me know in the comments below. But the other way we could write this, and this is the way that I do that in the classroom at least, you know, different instructors have different opinions, but one way that I can write the domain is by listing the values that x cannot be. I know x cannot be an integer multiple of pi. So n pi, where n is an integer. Typically when we write a domain, we write, you know, the interval for it, or we express what the domain actually is. This is writing what the domain is not. So technically I'm writing the complement of the domain. But anyway, I have to exclude any multiple of pi. 2. How about the range? Well, if I look at the graph, again, looking at the graph of the blue curve, these sort of parabola type things where they're bounded. It's not a parabola. Don't get me wrong, it's not a parabola, but it kind of has that sort of a shape. A lot of times students will be like, oh, that's a parabola. Well, it's not, but it kind of has that sort of a shape, so sometimes we'll call it like a pseudo-parabola or something, just to abuse the language. But anyway, the graph goes all the way down to, say, minus infinity. So I would have minus infinity up to minus 1. That is a point on the graph. And then union, the y values pick up again at 1, and then it's everything above. So this is union 1 to infinity. 3. The cosecant function has no intercepts. Okay, there's no x-intercept, there's no y-intercept. Because we can see there's no x-intercepts because the closest it gets from down here is minus 1. The closest it gets from up here is positive 1. There's no y-intercept because I can't plug in 0. Okay, so there's no intercepts for that. 4th, the period. That's always an important value to know with any trig function. Conceptually, the period represents how wide do I have to go to incorporate the most basic, to incorporate the pattern? What's the, well, I should say this rather than wide. How narrow can I be to incorporate the pattern? Certainly if I was to go just between 0 and pi, that would just give me this part of the graph. Well, we can see that this and this keep repeating. So what I need to incorporate is this parabola that opens upwards, this parabola that opens downwards. Again, to abuse the language there, that means I have to go from 0 to 2 pi. Therefore, the period is 2 pi. Okay. 5. When you talk about the sine and the cosine function, the concept of an amplitude comes up, right? The amplitude is, if I've got, let's do this over here. If we're talking about the function y equals 4 cosine of x, or y is equal to, say, negative 5 sine of x, the shortcut for the amplitude is to take the absolute value of the number out front. So the amplitude of this is 4, amplitude of this is 5. And we'll have, cosecant functions that we talk about that might look like this. I might have y is equal to 2 cosecant of x minus 3. Right? So I've got a transformation of the cosecant function. And you might think, well, the amplitude of this is 2. Well, in this case, the amplitude is not even defined because remember, what the amplitude means is this is half the length of the range. 4 cosine goes from minus 4 up to positive 4. The length of the range would be 8. Half of that is 4. However, for the cosecant function, we're looking at intervals that are infinitely long. So the length doesn't even make sense. So therefore, whenever we talk about the cosecant or the secant, the cotangent, sorry, I think I may have said that one twice. Cosecant, secant, tangent, cotangent, those have no amplitude. Or we could phrase it and say amplitude doesn't make sense for those types of functions. Okay. Let's take a look at a couple specific cosecant functions and find some basic information for those. Looks like I didn't dry that well enough. Sorry about that. Okay, so let's take a look at the following items that we want to find. Find the range and the period. Okay, so let's just find the range and the period for these two functions. All right, first and foremost, let's look at the range. The basic cosecant function is -1 and below, and then 1 and above. Now, if I multiply this function by 3, remember when I multiply a base function by a constant, if the constant is bigger than 1, then that is a stretch. So what happens is this -1 becomes -3, and this +1 goes up to 3, and then everything below that stretches down below, everything above that stretches up. So that means that 3 cosine is going to be -3 and below, and then 3 and above. So therefore, for part A, my range is -3 and below, 3 and above. Period. So it turns out we can use the same formula that we can for the sine function, meaning what I do is I take the period of the base function and I divide by the magnitude of the coefficient of x. Okay? That means I'm going to take 2 pi divided by the absolute value of b, where b is the coefficient of x. This would give me 2 pi over the magnitude of 2. Of course, the magnitude of 2 is 2. 2 over 2 is 1, so this gives me a pi. Now, if you remember your transformations, when I do anything on the inside of the base function, that's horizontal because it's changing the inputs. Inputs is horizontal information. And so multiplying this by a 2 is going to be either a stretch or a compression. This was a stretch, a vertical stretch. It's on the outside of the base function. On the inside of the base function, it's going to still be a stretch or a compression. We'll narrow that down here in a second. But remember that inside is always opposite. This is bigger than 1, so it's a stretch. This is bigger than 1, so it's a compression. And that should make sense if I tie this into the period, because the base function has a period of 2 pi, means its pattern is between 0 and 2 pi. When I multiply that by a 2, this 2 right here cuts the period in half. So that must mean that this same pattern has to appear within an interval of length pi rather than 2 pi, so we compressed it. Okay. Part B. The range of the function. Okay, so let's talk through this one. The basic cosecant function is, let's start with the bottom, because this is broken into, the range is broken into 2 pieces. Let's do 1 piece at a time. I know that the base function is -1 and below. So if I take -1 and below and I multiply that by a 4, that's going to be -4. So it starts here -1, now it's going to be -4 and below. And then when I take -2 and I subtract that, that means that the bottom of the range is going to be down to -6. So this is going to give me -infinity up to -6. All right, let's look at the top portion of the range. The top of this, the top of the cosecant is at 1. I multiply that by a 4 to go up to 4. And then I subtract 2, which means that 4, that would be sort of the vertex here, that up at 4 is going to drop down to 2. So that means that the bottom of this part is going to be 2, and then off to infinity. Similar for the period, we take 2 pi divided by the magnitude of b. B in this case is 3, so I've got 2 pi over 3. So 2/3 of pi. Again, that is a horizontal compression because the period is smaller than the period of the base function. And again, I've got a 3 on the inside. That makes that a horizontal compression, not a horizontal stretch. This is a stretch because it's bigger than 1. This is a compression because it's bigger than 1. This is on the outside, that's vertical. This is on the inside, that's horizontal. Okay.